Hey everybody, so today we are just going to do a short extension of the simplifying nth roots unit that you looked at a few days ago. So this time I'm going to simplify an nth root, but now I'm going to add a variable inside. So we're just going to do some basic types of simplifying nth roots. I'm going to ask you to simplify like the square root of x squared. We actually know what that is already. Or the cube root of x to the 36. So like, how do you simplify nth roots of variables that have exponents? So really, I think the easiest way to kind of do this is you just ask yourself, how many groups of n, which is the index, are in M? The number of groups that you can make is the exponent of the variable that comes outside of the radical. If there's any remainder, like if there's any amount that can't be made into a group, then that becomes the exponent of the variable that's left on the inside of the radical. So we already know from our quadratics chapter, every time I would say, okay guys, what's the square root of x to the second? You guys always told me that was x. Okay, so if I kind of use this rule up here, remember a square root, we don't write it, but the index is 2. So this is really like saying how many groups of 2 can you make out of 2? Well, I can only make one group. Okay, if you look at my second example, the square root of x to the 12th, my index is 2. Okay, so if you think about it, how many groups of 2 can you make out of 12? I can make 6 groups. So my answer is x to the 6th. So the square root of x to the 12th is x to the 6th because I can make 2 groups. I can make 6 groups of 2 out of 12. Hopefully you're kind of seeing a quick shortcut. Right? How can I get a 1 from a 2 and a 2? How can I get a 6 from a 2 and a 12? Well, you're really just dividing. So really, you're just going to divide the exponent by the index. Okay, this is a real shortcut. All right, so 2 divided by 2 is 1. 12 divided by 2 is 6. Okay, so in these two cases, we didn't have a remainder. All right, so there was nothing left inside the radical. So if I add a number inside, okay, you're just going to simplify it the same way we did last time. So why don't you take a minute and see if you can simplify the square root of 81, x to the 16th. All right, and if we kind of break this up piece by piece, well, the square root of 81 is 9. Now if I look at x to the 16th, again, I'm taking a square root. I don't want to take the square root of 16. I want to use my rule up here that says take my exponent and divide it by the index. So 16 divided by 2 is 8. So you're left with x to the 8th. There was nothing left. There was no remainder, so there is nothing left inside the radical. The radical is totally gone, right? 81 was a perfect square. Square root of 81 is 9. The exponent 16 divided by 2 came out as 8. There were no groups left. If you look at my last example with square roots, okay, this time I'm taking the square root of x to the 23rd. So again, there's an index of 2. Okay, so if I use my rule, 23 divided by 2 is 20, and there's a remainder of 3 left over. Or if you think about it, if you have 23, right, you can make 10 groups of 2, and there's going to be 3 left over. So 23 divided by 2, there's 10 groups I can make, so that x to the 10th comes out. Inside the radical, I'm left with that remainder of 3, right? 23 divided by 2, okay, there was 10, and a remainder of 3, if you kind of think of it like that. Okay, so the 10 becomes your exponent of the variable that comes outside. The remainder that's left over is the exponent of the variable that's on the inside. So as soon as that exponent is not divisible by your index, you're going to have some type of variable left on the inside. Okay, if I look at my cube roots, all right, so the cube root of x to the 3rd, well, we kind of already know that one too because we did perfect cube factoring last chapter, right? The cube root of x to the 3rd, you guys would always tell me, well, that's just x. And again, if I kind of use my rule, now that we think about it this way, 3 divided by 3 is 1. Or how many groups of 3 can you make from 3? Just 1. All right. If I take the cube root of x to the 36, all right, now again, 36 is an exponent. So I want to divide 36 by my index. Well, 36 divided by 3 is 12. There is no remainder, so my answer is x to the 12th. Okay, the cube root of x to the 36th is x to the 12th because 36 divided by 3 is 12. All right. Why don't you take a minute and look at this next one. The cube root of, I'm going to add a number inside, 216, x to the 27th. So why don't you simplify it the same way you did up here. So take a minute, use your table of powers if you need to, and simplify the cube root of 216, x to the 27th. Okay, and hopefully if you're using your table of powers, right, the cube root of 216 is 6. And 27 divided by 3 is 9, no remainder. So my final answer here is 6x to the 9th. Okay. All right. And then again, here's another example where, okay, I have x to the 17th. I'm taking the cube root of that. Well, 3 doesn't divide into 17 evenly, but that's okay. All right, we're just going to simplify it. So I'm going to say, all right, well, 3 goes into 17 how many times? It goes in 5 times. 3 times 5 is 15, and there's a remainder of 2. So I'm left with an x to the second inside. Okay, or you can think of it, how many groups of 3 can you make out of 17? I can make 5 groups, but there's going to be 2 that are left over. Okay. All right. We can do the same thing with the 4th root. All right, so I can kind of just keep adding on indexes, and the rule is still the same. So if I take the 4th root of 81, x to the 24th, right, you guys just want to be careful that, again, you're taking a 4th root and not a square root. So x to the 4th root of 81 is 3. Okay, x to the 24th, well, 24 divided by 4 is 6. There's no remainder. So my answer is 3x to the 6th. Okay. All right. And my last example has to do with a 4th root. All right. I'm taking the 4th root of x to the 35th. Okay. Well, 4 does not divide into 35 evenly. Okay. But 4 does go into 35 8 times. So I have x to the 8th. All right. With a remainder of 3. So I will have an x to the 3rd left inside. Okay, or how many groups of 4 can you make out of 35? I can make 8 groups, but there's going to be 3 left over, so they're inside. Okay, and we can really apply this with any index. So what if you take the 7th root of x to the 15th? Why don't you take a minute and simplify that expression? Okay, and we're using the same rule. 7 divides into 15. It doesn't go in evenly, but 7 does divide into 15 2 times, okay, with 1 left over, so I'm going to have an x on the inside, right? Or I can make 2 groups out of 7. I can make 2 groups from 15 out of 7, and there's going to be 1 left over. So my final answer is x to the 2nd, 7th root of x.